Okay, so let me start by reminding you of the last thing that we proved, and that is the Curry-Theodori theorem. And here X was metric space. X was a metric space, and mu is an outer measure on X with the property that it's additive on sets that are a fixed distance apart. So remember, the picture of that is simply this. This is A and this is B, and there has to be a positive distance in this condition. And then the conclusion was that mu is, then all Borel sets are mu measurable. So we gave the proof of that. And a very nice theorem, because it enables you to check rather easily that many of the measures that you come across in practice, and many of the outer measures that you come across in practice do have this property, that all the Borel sets are mu measurable. Let's do one example, since it's an easy example. The example that I want to mention is the Lebesgue measure on Rn. So this is the case when mu equals Ln, which is Lebesgue measure on Rn. Now let me just remind you, I know of course you know about Lebesgue measure, but let me remind you about a couple of things. First of all, recall the definition of Lebesgue outer measure. It's defined by taking, for any set A contained in Rn, you define Lna to be the infimum over all sums of the form sum volume of Ij, j equals 1 to infinity, where I1, I2, etc. are intervals, open intervals. Now remember, an open interval in Rn is just like an open interval on the real line, except that you take the Cartesian product of those. So you get A1, B1, A2, B2, up to AN, BN. And the volume of I is just the product of the edge lengths. So that's the product B1 minus A1 times B2 minus A2, etc., up to Bn minus An. And you take the infimum over all possible collections with the A contained in the union. So of course you know that. But you probably also know that you can give a modification of this and give an alternate definition where you say, if you take one of these intervals, in the case n equals 2, it would look like that. You could always subdivide that into rectangles, sub-intervals where the diameter is less than delta. Now you could object that those sub-intervals aren't open, are they? Not necessarily, but you can always enlarge a little bit without increasing the volume very much. So you can actually assume here you get exactly the same result if instead of this you also throw in the stipulation that diameter of Ij should be less than delta for every j. Doesn't change anything. Gives you the same result. You can check that. So This is for any delta positive. Now, if you think about that, let's go back to this condition for this particular outer measure. Well, we're covering these things by rectangles of lots of rectangles of diameter less than delta. If these things are bigger than delta distance apart, or in other words, if we take delta less than the distance between the sets, then clearly that's additive. So very easy to check using this modified definition. It's very easy to check. I'll just leave it as an exercise for you that this condition is satisfied for Lebesgue measure. If distance from A to B is positive. But you see, that's great because it means we can apply this Curry-Theodori theorem immediately. You don't have to do any work at all. That's a good idea in general, right? Or maybe not, but still. We can simply read off immediately that all the Borel sets are indeed Lebesgue measurable. You've probably seen a proof of that, but it may have been a bit more complicated than this proof. So, hence, all Borel sets are Lebesgue measurable. That is measurable with respect to the Lebesgue outer measure. Yes. Okay, thank you. I'm too weak, huh? I need a... That's a polite way of saying it. Okay, we've got to turn it on. It's an idea. Maybe it is on. Yeah, I think it's on.
But this microphone maybe is too low.
Oh, okay.
Yeah, you want to lower it a little bit.
Yeah, that may be better. Or maybe not.
In here.
Yeah. We can't put it, yeah, okay. Does that work? Okay.
Does it work?
I think so, yes. At least psychologically I believe it works, and that's all that's important. So I wanted to mention that first up. So that's a nice application of this Curry-Theodori theorem, very nice. We'll give another very important application in a minute when we talk about Hausdorff measure. Okay, so that's the first topic for today. And, I meant to remind you, do keep in mind that the text for the course, text plus some additional stuff, including the current assignment problems, if you want to do those problems. Plus solutions to the current assignment. Oh no, actually solutions to the previous week's assignment. Is on the web page, math.stanford.edu /LMS, that's my initials, /NTU. Find some stuff there, including the text. Okay, so that's our first topic for the day. That's a nice one. And notice also, there's another point here that's rather important. If you look at this definition, notice that you're taking the infimum of these things. And that means that actually it's clear from here that LNA, rather important additional note that follows direct from the definition, LNA is actually, this union is an open set, you see, and you can get arbitrarily close. by subadditivity of the outer measure, this is arbitrarily close. In fact, the measure of that is less than or equal to this sum, you see? So you can get arbitrarily close to the Lebesgue measure by using these open sets. So that means in particular that LNA turns out to be the same as the infimum, inf, taken over U open with U containing A of LNU. That's often referred to as a regularity property of the measure, that you can approximate the measure by taking open sets which contain the given set. And I want to show, the next thing I want to show today is that there's actually a much more general theorem. There's a much more, a similar principle applies to a much more general class of measures. So let me explain that theorem. So here's the theorem. Suppose mu is a Borel regular, so X is a metric space. And mu is any Borel regular outer measure. Outer measure on X. And suppose that there's one condition here on mu. That is one extra condition other than the Borel regular. By the way, let me remind you, in case this is a new concept, we did talk about this last time, but in case this is a new concept, let me remind you what this means. It means two things, right? It means that all the Borel sets are measurable, mu measurable, and given any set, you can always find a Borel set containing that set with the same measure, right? That's the meaning. So take any such measure, and suppose that U is so-called, here's a bit of jargon that we have to get used to. Suppose that mu is open sigma finite. I'll explain what this means in just a second. So open sigma finite. That means that there exists a sequence of open sets in the metric space such that the union, such that these exhaust the whole space, so the union j equals 1 to infinity vj is the whole space, and mu is finite on each of these open sets for every j. Of course, for example, Lebesgue measures are like that, right? You can take an increasing sequence of open balls. They've all got finite Lebesgue measure, and the union of those balls is the whole of Rn. So it's a fairly natural concept. Of course, one important case of this is when the measure is in any case finite. That's an important case also. So keep that case in mind. In fact, that's the key case to think about. So they're the hypotheses. Then you get a result very similar to this result that we got for the Lebesgue measure. That there are in fact two conclusions here. That the measure of any set A is indeed equal to the infimum taken over U open, U containing A, of mu of U, and that's true for every set A contained in X. So that's nice, exactly like this result, precisely this, but it's much more general. And the second thing is that if you take a measurable set, then you can notice this one says that you can approximate the measure by using open sets which contain the thing. This second one is going to say that you can approximate the measure by using closed sets contained in the thing, right? So mu A equals a sup over C closed, C contained in A of mu C. And that's not true for every A, but it's true for every mu measurable A. Notice this first one doesn't require that A be measurable, so it's true generally. Okay, so let's give the proof of this. Since I'm a bit short of time, I'll just do the main step in the proof, which is to prove this one in the special case when mu x is finite. To handle a general case, you apply that particular case to mu restricted to these open sets. So I'll leave you to check that detail, but I'll give you the main step of the argument. So main step in the proof. So assume that mu x is finite. And actually, this is a clever proof. It's not the sort of thing you would immediately think of. It requires, it's very clever. So well, before we start, let's make an observation first. Notice it's sufficient to prove this just for the Borel sets. Why is that now? Well, you see, if you take an arbitrary set A, you can always find a Borel set which contains it with the same measure, right? So it doesn't change this side, and this side, in any case, is bigger than it was before. And if you can prove it, therefore, for that, then you've proved it for the original thing, trivially. So assume that, and without loss of generality, assume that this is the proof of one we're talking about. Without loss of generality, assume that A is equal to a Borel set. And as I said, now there's a clever argument. You let script A be the collection of Borel sets A such that this indeed is true. Let's label this number 1, such that number 1 is true. So it's a collection of Borel sets such that 1 is true. Now notice that all the open sets trivially satisfy 1. There's not much to check there. See, if A is already open, then you clearly get the inf just by taking U to be equal to A, right? So that clearly. So this clearly contains all the open sets. And we'd like to say that we're finished now, because that would then be the sigma algebra, which contains the open sets, contains all the Borel sets, by definition, because the Borel sets are the smallest sigma algebra, contain all the open sets. But there's a catch. We don't know that this is a sigma algebra. It's defined in this funny way. So we want to somehow remedy that. Well, what we note first of all, in fact, let me claim something. I claim that at least this set A is closed under taking countable unions and intersections of sets. So closed under countable unions and intersections. Well, let's check that. Let's do the unions first. So suppose, we've got to check that closed under countable unions. That means we've got to take a sequence of sets in A, and then we've got to prove that the union of those sets is also in A, right? Well, if those are in A, we can certainly find open sets that get arbitrarily close. Whereas saying it's in script A means that this is satisfied. So we can get as close as we like to the measure using an open set. So there exists open U1, U2, etc. with the measure of Uj with, yes, these are sets which contain the relevant A. So Uj contains Aj. and the measure of uj minus aj is less than epsilon. In fact, take epsilon bigger than 0 at the beginning given. In fact, I can do better. I can make it as small as I like. I don't have to use epsilon. Let me use epsilon over 2 to the j, because we're going to do a sum in a minute. So now let's check that this claim is correct, that the union is, in fact, can be approximated also, that this property is also true for the union. Let me get this up here. So let's try that. So what do we know about the union of aj relative to these uj's? So observe that the union of the uj's, say union from k equals 1 to infinity minus the union j equals 1 to infinity. Aj. I claim that's got small measure now, and then we'll be finished if that's true, because this is an open set. The countable union, a union of open sets is open. Well, let's see. This is contained in fact, it's equal to the union k equals 1 to infinity of uk minus the same union, j equals 1 to infinity, aj. And that's certainly contained in the union k equals 1 to infinity of uk minus ak, because union aj clearly is bigger than union of ak, so certainly that's correct. And so the measure of this difference, by subadditivity is less than or equal to the sum of the separate measures of these. And that's less than, let's see, that's less than, we chose these so that they were less than epsilon over 2 to the j. So this is less than epsilon times the sum k equals 1 to infinity 2 to the minus k, which is equal to epsilon. So that's good. That does the job. So that means that this union is, so we've shown that it's closed under countable unions. We still have to check countable intersections. Well, that's a similar argument. I won't do it. I'll leave you to check that. So let's assume we've checked that one. No harder. Well, there's one little twist. You should think about it. You'll see there's one little extra twist involved in that, because one slight complication in checking intersections is that the intersection of open sets is not necessarily open unless it's a finite intersection. So you have to worry about that, but it's easily fixed. You just take a finite intersection instead of a countable intersection. But anyway, I'll leave you to check that since we're a little short of time. So let's assume that we've checked both of these now. And so we've got this collection that we started off with is now closed under countable unions and intersections. Now, it's still not a sigma algebra because it's closed under countable unions. That's one of the properties of sigma algebra, and it certainly contains the empty set in the whole space. In fact, it contains all the open sets, as we mentioned before. So the only property that we're worried about now is the complementation property, right? Whether or not A being in the set implies the complement of A is in the set. Now that's not obvious at all from the way this is defined. So we have to be clever here. So we define, this is sort of a clever idea, we define A tilde to be the set of A in script A such that the complement is in script A also. Now notice that, well, this is non-empty at least, because the empty set and the whole space clearly are in this collection, this new collection. So phi and x are certainly in A tilde. It's not clear that the open sets are in A tilde. They're in A, but we don't know that they're in A tilde because the complement of an open set is closed, and we don't yet know that the closed sets are contained in this collection. So on the other hand, take an open set then x minus u, let's call it C, is closed. X minus C is closed, and we're in a metric space. And think about this. If you take a closed set, you can always write C as the intersection j equals 1 to infinity of the set of points in the space such that the distance of the point to the set C is less than 1 over j. Right? That's just saying that the C is closed, so it's the same as the set of points at distance 0 from C. It's a closed set, has that property. It's the same as the set of points at distance 0. That's the intersection of the set of points at distance less than 1 over j from C. But notice that these are all open sets. So this is a countable intersection of open sets. So this is in A, because we proved that A is closed under countable unions and intersections. So that means that we've checked not only that U is in A, but its complement is also in A. So that means that then that U is in A tilde, because we proved that both U and its complement is in A. A clever argument. If you haven't seen that argument before, I probably went through it a little too fast. But think about it. It's a very clever argument. You may want to think about that argument. So that proves that A tilde that proves that A tilde contains all the open sets. So A tilde contains all the open sets. Now, we still haven't quite finished. We haven't yet shown that I claim that A tilde is a sigma algebra. So that's the final step in this proof. So let's think about that. So take right. Yeah. So yeah. So claim A tilde is a sigma algebra. Okay, let's remind ourselves what the properties of a sigma algebra. The empty set and the whole space have to be in it. That's the first property. Well, we've already pointed that out. Second property is that complementation. If A is in the set, then the complement of A is also in the set. But by definition, that's true here. So that one's okay. So the only one to check is that if you take the third property, we just have to check the third property, that if you take a sequence in A tilde, then the union of them is in the set also, set A tilde also. So let's check that. So, the union, yes. So, first of all, the union of AJ, j equals 1 to infinity, is certainly in A, because A tilde is contained in A, and A is closed under countable unions, right? So certainly the union, that's okay. And what about the intersection now? So we're trying to prove that. So we've checked that the union is in A. In order to say that the union is in A tilde, I've got to check that the complement of this is in A, right? That's what we have to check. That's this thing. So let's check that. So let's look at the complement. And X complement union J equals 1 to infinity of AJ. Well, by definition, that's De Morgan's laws. That can be written as an intersection J equals 1 to infinity of X minus AJ. And that's great, because each of these is in A, of course, because each AJ is in A, and then the intersection, A is closed under countable unions and intersections, so this is in A. So both the countable union and its complement are in A. Of course, that means that the countable union is in this thing A tilde. So that's it. Then A tilde then, so A tilde contains all the open sets. We check that here. And it's a sigma algebra. We check that here. So it contains all the Borel sets. Contains all Borel sets. And of course that means that, so all the Borel sets, A tilde is contained in A, so it's so A in particular contains all the Borel sets, because A tilde is a subset of A, that contains all the Borel sets, so script A contains all the Borel sets, and that's it. So that's all we had to prove. So you see, that's not so easy. It's a clever argument. On the other hand, it's a fairly deep result. It's not a trivial result, very useful result. So that takes care of part one. And part two is rather easy. You just get part two by applying part one to the complement of A and using the fact that the complement of an open set is a closed set. So it's rather easy to check two now. So I'll leave that to you because we're getting a bit short of time. Okay, so that's the theorem. It's a very nice theorem, very important theorem. All right, so I think we can go on now. I think that's all I needed to say in the abstract sense. Now I think we can talk about Hausdorff measure now. So let's now get a bit more concrete. So let's give a definition of Hausdorff measure. Maybe this is better. I'm getting my exercise. I really don't know what I'm doing, right? Right. Okay, so let's try this one. Okay, so let's set up some notation. So I'm going to let omega n, I'm going to let that be an abbreviation for the Lebesgue measure of the unit ball in Rn. This is the unit ball in Rn. Closed unit ball in Rn. Now, you've probably seen this in in your previous experience, that there's an exact formula for that you can prove by induction and Fubini's theorem using induction on n. There's a formula for that. It's actually pi to the n over 2 over the integral from 0 to infinity of t to the n over 2 times e to the minus t dt. Hope I got that right. I think that's correct. This is you'll recognize this bottom line as a gamma function. Actually, it's the gamma function of n over 2 plus 1. It's a gamma function. And now, even if n's not an integer, we're still going to use this formula. I'm still going to take this even if n is fractional. So sets up the notation. So that's what I'll always mean by omega n. I just mean that constant. Now, here's the definition of Hausdorff measure. You take a delta positive, and X is any metric space. And n bigger than or equal to 0. N does not need to be an integer. Not be an integer. It can be fractional, that's okay. In fact, that's rather important in some applications. Then we define the following. We define this quantity script hn delta. This is usually called the size delta approximation of Hausdorff measure. That's the jargon. Size delta approximation. Hausdorff measure. Of course, that doesn't mean much yet because we haven't said what Hausdorff measure means yet, but that's the jargon anyway. That's what you. And then you define Hn for any A in X, contained in X, any subset of X. You define Hn delta of A to be simply equal to the infimum of a sum. Omega n is just a sort of a normalizing factor times the sum j equals 1 to infinity diameter of Cj over 2 to the nth power. Oops. Okay, so that's the where the nth is taken. It's sort of analogous to the definition of Lebesgue measure, except instead of intervals we're using sets, Cj, where the nth is taken over all collections C1, C2, etc. with, well, of course, they've got to cover A, just as they had to, just as the intervals had to cover A in the definition of Lebesgue measure. So these sets have to cover A in the definition of this quantity. And one further condition, and diameter of Cj less than delta for every j. These are arbitrary subsets of Rn. Nothing special about that. They don't have to be open, closed, or anything. They needn't be convex. They needn't be anything. In fact, convexity doesn't make any sense here because we're in a metric space, right? So just any sets. Any sets. The only restrictions you put on these is that they have to cover A, and they have to, each one of them has to have diameter less than delta, right? Other than that. So that's the definition of size delta approximation to Hausdorff measure. Now, that looks a little weird at first, but let's check a couple of things. So, note, first thing to note is that it's pretty clear that this is an outer measure on X. You can check that. You remember, to check that something's an outer measure, what did we have to do now? Let's see, there was a couple of properties that had to be checked. Firstly, the measure of the empty set has to be 0. Well, that's obviously true here. Secondly, that if A is contained in B, then the then the quantity of A is less than or equal to the quantity of B. Well, that's trivially true also from this definition. And the third thing is subadditivity. If you take a countable union of sets A, then this quantity applied to the union is less than or equal to the sum of the quantity applied to each one. And that's very easy to check too. It's very similar to the argument that you use to check that Lebesgue measure is an outer measure. So I'll leave this as an exercise. So exercise, check that Hn delta is an outer measure on X for each delta bigger than 0. Okay. And so that's the first thing. At least it's an outer measure. And then the second thing is we can go back and use Curry-Theodori's theory again. Notice that trivially, it's very easy to check just using exactly the definition. Using this definition, it's obvious that if you have two sets, A and B, which is separated by a distance of at least 2 delta, then this is additive on those two sets. It's just trivial to check that using the definition. So, distance from A to B bigger than 2 delta implies that Hn delta A union B is equal to Hn delta of A plus Hn delta of B. So that's great because now we can apply Curry-Theodori's theorem. So Curry-Theodori Curry-Theodori's theorem then implies that all Borel sets are measurable. Oh, sorry. I forgot that we haven't defined Hausdorff measure yet. So let's go back. So here's our definition of size delta. Now, let's think about this. I'll come back to that in a second. So let's think about this. Hn delta of A is defined in this way with this condition, that the diameter of each Cj should be less than delta. Now notice that if you increase delta, that means the inf goes down, right? Because you get a bigger collection of sets that you're looking at. So that means this is an increasing function of delta, but that's not a good way to think of it. The way to think of it is that this is a decreasing function of delta, but that's not a good way to think of it. It's better to think of it as an increasing function as delta decreases. As delta decreases, it's increasing, right? So that's the second remark. Hn delta A increases as delta decreases. Now it could tend to plus infinity even if it's not already plus infinity, right? But that doesn't matter. Our outer measures are allowed to take value plus infinity. So then we can define. It makes sense then to define, and this is the definition of Hausdorff measure. You simply define Hn of A to be the limit as delta tends to 0 of this. Now notice that makes perfectly good sense because, as I said, this is a monotone quantity. So therefore it does definitely have a limit, but keep in mind the limit may be plus infinity. That's fine though, we don't care about that. So that's that. And again, a similar exercise, check that Hn is an outer measure. Again, very easy to check. So I'll leave you to check that one. So we've got an outer measure now, which is the limit of these quantities, Hn delta. Okay, let's go back here now. So we have this observation that if you take distance A to B bigger than 2 delta, then this is additive. Now that means in particular that DAB bigger than 0 implies that Hn A union B equals Hn A plus Hn B. Additivity, as long as the distance is merely positive. Because if it's positive, it's bigger than 2 delta for some small enough delta, and that means you can apply this for small enough delta. Now just take the limit of each side as delta tends to 0. So very easy to check. Just take limits as delta tends to 0 of this identity here. So that's great. That means that we've got the Carry-Theodori restriction. So Carry-Theodori's theorem Carry-Theodori's theorem implies, no, not quite yet. Okay. Carry-Theodori's theorem implies that all Borel sets are Hn measurable. That's great. So Hausdorff measure has that property. Be careful. Almost no sets are measurable with respect to this guy. For instance, there are frightening counterexamples. For instance, if you take a half space, except in the case when n is in, if n is, for instance, if we're in Rm with m bigger than n, then almost nothing is measurable with respect to this guy. It's really bad. Even a half space is not measurable with respect to this guy. You can check that very easily by an example. So, but that doesn't matter. We're interested in the actual Hausdorff measure, Hn, and all Borel sets are Hn measurable. So that's good. Okay, so, right, so that's good. Let's take a 10-minute break and we'll start again at 1:30. What did she say?
Because I collect homework.
He said to collect homework for you today.
Oops. I think I just did something bad. Yeah, go for it. Is it all right?
我们有在那边关掉。
Yeah. Okay. Oh, thank you. You're depriving me of my exercise. Thanks. Okay. All right, now let's talk about one extremely, so we now know about Hausdorff measure, but let me describe one extremely important special case. The special case is when x, remember that was any metric space. Special case is when x is just equal to Rn. And when we're talking about n-dimensional Hausdorff measure in Rn, notice that, same. So this is I want to talk about that special case when we're talking about n-dimensional Hausdorff measure in Rn. Of course, we could talk about m-dimensional Hausdorff measure in Rn, where m is less than n, but this case is interesting, and I want to show you that actually Hn is the same as Lebesgue measure. It's not obvious, of course, because of the definitions are slightly different. But so the claim is if x equals Rn, then Hn delta is the same as Hn, and they're both the same as Lebesgue n-dimensional measure. So, very nice fact. Notice that's the only time, this is really sort of the only time this behaves nicely. Usually, as I said, this is a horrible thing. It's usually almost nothing's measurable with respect to this for positive delta. But on the other hand, in this case, it's the same as Lebesgue measure. So let's give the proof of this. And the proof it requires a few steps and at least one clever idea. First of all, you prove the inequality H I want to show that Hn delta is less than or equal to Ln. That's the first step in the proof. So take I1, I2, etc. to be open intervals. Just as in the definition of Lebesgue measure, open intervals. And so A is any set. And take open intervals with A contained in the union. And at this, let's also throw in the condition that diameter of Ij is less than delta. So here delta is positive given. So we're given a set A and a positive delta, and then just take open intervals like that. All right. I'm going to make one interesting point here about Lebesgue measure. If you take an open set U, it's a little bit surprising at first sight, but you can actually find pairwise disjoint closed balls inside U whose union has the same measure. That's not obvious, is it? In other words, there are no gaps. There are gaps, but they have zero measure, you see. So the claim is there exists closed balls. B1, B2, pairwise disjoint. Bi intersect Bj empty for every I not equal to j, and Hn and Ln of U minus the union of Bj. These are balls contained in U, as in the picture. And the claim is that you can chew up all of the measure at 0. It's not at all obvious, right? In fact, it's one of the assignment problems for this week to check that that's true. You do it by dividing, getting cubes, first of all, that chew up all the measure, and then inscribing a ball inside each cube to chew up a fixed proportion of the measure first, but then you've got to iterate that process. So it's not obvious, but it is true that you can do that. So you can do that here. So you can do that for each of the ij. So pick for each I, for each j, pick pairwise disjoint. I don't want to keep writing pairwise disjoint, so I'm going to abbreviate that. That's PWD, right? Pairwise disjoint. Save a bit of writing. So pick pairwise disjoint balls Bi, Ji, I equals 1, 2, etc. with union with Ln Ij minus the union I equals 1 to infinity Bij, Bji equals 0. That's this result with this in the special case when U is this interval Ij. Okay, and notice that this implies that Hn delta of Ij minus the union I equals 1 to infinity Bji is also equal to 0. That's not hard to prove. Just look at the definition of Hn delta, very similar to the definition of the Lebesgue measure, except that we're using arbitrary sets. Well, if you're trying to prove measure is 0, you can use the same intervals that you used for the Lebesgue measure. You can make those volumes arbitrarily small, and that'll also work for this Hn delta. So it's very easy to check this, right? You can do that. So both of these have measure 0. And then, right, so then volume, so then, yeah, so, okay, what do we do here? I've forgotten. Okay, so the volume of Ij then, of course that's just the Lebesgue measure of Ij, is equal to the sum of the Lebesgue measures of these balls. Like so. And yes. Okay, and that's now, well, of course, the Lebesgue measure of a ball is the sum, and the Lebesgue measure of the ball is omega n times the radius to the nth power, right? Radius to the nth power, omega n. But remember how that's how omega n was defined, the volume of the unit ball. So this is omega n times the diameter. Now the radius is the diameter over 2 to the nth power. And furthermore, each of these Ij's has diameter less than delta, so each of the Bij's, of course, must have diameter less than delta too. So that means these are some of the candidates that, so that means that by definition of HN delta, notice this, the HN delta is defined to be the nth of coverings, right? So this is HN delta of the union of the balls. By definition of this, see, this is just these are just, see this set here, it's covered trivially by the balls themselves, and then the HN delta is defined to be the nth over all possible coverings. This is just one possible sum in that nth, so that's certainly an inequality that's correct, and we have that. So now let's just sum over J as well. And yes, and now remember I said that it's also true that HN delta of the difference is measure 0, so this will give us HN, I'm sure I'm doing this right. So far everything I've said is correct, but I'm not sure it's what I wanted to say. HN delta ln, right. HN delta, oh, I see. Yeah, so so this is by subadditivity, this is bigger than or equal to HN delta of the union over I and J, Pij. Now, this union covers all of A except for a set of measure 0 by this, HN delta measure 0 by this fact. So this is bigger than or equal to HN, in fact it's equal, yes, this is equal to HN delta of A. So we have HN delta of A is less than or equal to the sum of these volumes. So less than or equal to the sum volume of Ij. Now that was for all possible open intervals with diameter less than delta, but remember if we take the nth now, so simply take the nth of each side over all such collections Ij. And then this side gives you the Lebesgue measure. So that tells you that HN delta of A is less than or equal to the Lebesgue measure of A. So that's good. Just by fiddling with the definitions you get that. So we didn't really have to do very much. The only tricky thing there was to use this fact about balls, pairwise disjoint balls, chewing up almost all of a given open set. But now the reverse inequality requires a result that's rather interesting in itself. It's called the isodiametric inequality. So before we give the proof of the reverse inequality, let me discuss the isodiametric inequality. Okay, that goes as follows. Take any set A in Rn, then the Lebesgue measure of A is less than or equal to omega n times the diameter of the set A over 2 to the nth power. Which looks a little weird at first sight, but you see, notice equality holds here if you take a ball. See, if you take a ball, then you've got equality, because this is the volume of the ball, if A is a ball. Diameter over 2 is the radius of the ball. So, equality with A equals a ball. In fact, that's the only way you get equality. So, that's why it's called the isodiametric inequality. See, another way of saying it is that out of all sets of a given diameter, the one with the largest volume is the ball of that diameter. Out of all sets of a given diameter, the ball has the largest volume. So that's why it's called the isodiametric inequality. And let me give the proof. First let me give you a false proof. Before we start, let's observe that without loss of generality, we can assume that A is compact. It's enough to prove it for A compact, because then it follows generally. You see, the point is if you take any set A, you can always take the closure of A. That's got the same diameter, but it's got bigger Lebesgue measure. So if it's true if this inequality is true for the closure, then it's trivially true for the original set as well. And A can also be assumed to be bounded, because if A is not bounded, this side is in any case plus infinity, and there's nothing to prove, right? So we may as well assume A is compact. No problem. So suppose our set A is here. Since A is compact, we can always find points X and Y which give you the diameter. They actually attain the diameter, the maximum distance apart. So pick X and Y in A with a distance from X to Y equals the diameter. No question about that. You can do that. Diameter of A. Certainly you can do that. And then it's very easy. You simply take the line segment joining X and Y and pick a ball, take a closed ball, with one of its diameters equal to this line segment. Equal to the line segment joining X and Y. You can certainly trivially do that. And then we're done, because here's B, here's A is contained in B, so the Lebesgue measure of A is less than or equal to the Lebesgue measure of the ball, which is diameter of A over 2 to the nth power times omega n. Of course, that's obviously a false proof, right? Because the picture is misleading. For instance, consider the equilateral triangle. Here's the diameter. If you put a ball of radius that, see, that doesn't work. Leaves out a bit here. That doesn't prove the statement's false, that only proves my proof is false, right? But the statement's not false for this example at least, because you can always take this little bit out there and transplant it down to here. And that, nice, right? You still, so the inequality is still correct for that example, but the proof is not. So we have to become more clever in the proof. So let's. This is where we need Steiner symmetrization. Very clever idea. Steiner symmetrization. So let me explain what that is. If you take a point xi in the jth coordinate plane, xj equals 0. xj is the jth coordinate in Rn. And let then Lj xi be the line segment normal to the jth coordinate plane passing through this point, right? So this is the set of xi plus t times ej, where ej is the jth standard basis vector, such that t is in R. So use that notation. And yeah, I wanted to say something else about that. Oh, I'll think of it in a minute. And we've got our set A is compact, we're assuming. And then we define the Steiner symmetrization of A. Formally it looks funny, but I'll draw a picture and you'll see that it's really very natural. This is the union over all xi in the jth coordinate plane union over all xi such that this line, this is a line normal to the jth coordinate plane, right? Such that that line has non-empty intersection with A. And up here we take the set of xi plus t ej. Now here it's a symmetric closed interval. It's going to be, the condition is that mod t is less than or equal to half the Lebesgue measure, one-dimensional Lebesgue measure. By the way, that's what I wanted to say. Let's let pi be the projection of this line onto the real line that gives you just t. So pi of xi plus t ej equals t. So let's agree on that. Pi is the orthogonal projection of this line onto the real line. And such that the Lebesgue measure of that projection over 2, that's the length of this interval, A intersect Lj xi. Now what on earth does that say? Let's actually draw a picture here. It looks horribly complicated, but you see it's really very boneheaded. If we have a set here, I don't want to make it too complicated, and then here's the jth coordinate plane, xj equals 0, then it's saying that we replace that line segment, this is the xi, here's the line Lj xi, coming down through xi, orthogonal to xj equals 0. We take that line segment and replace it by a symmetric line segment of the same length, but symmetric about the origin here, down here. And we do that on each of these cross sections, right? So you see what the picture looks like. It's the Steiner symmetrization of this guy looks something like this. It's a bit big. I don't know. Something like this, but it's symmetric. Something like that. So that of each of these, that length there is the same as that length up there above. It doesn't look like it's the same, but that's my bad artistry. Okay, so that's the Steiner symmetrization, and I think it's one of the assignment problems this week that check that if A is compact, this is also compact. And furthermore, the Lebesgue measure of the Steiner symmetrization of A is in fact the same as the Lebesgue measure of A. So it doesn't change Lebesgue measure. Now this one we can prove trivially. You see the proof? Fubini's theorem. You just use Fubini's theorem, integrating in the jth coordinate direction. According to Fubini's theorem, you integrate these line segments over the jth coordinate plane, you get the measure of the set. And in each case, you get the same answer when you integrate over these line segments, the same length. So this one's trivial. That's, by definition, true. So it doesn't change Lebesgue measure, but on the other hand, it does give you something symmetric. This is symmetric in the jth coordinate. Sj A is symmetric in the jth coordinate. By construction, you see it's symmetric in the jth coordinate. This is the jth coordinate axis coming up this way, right? The xj equals 0 is here. So symmetric in the jth coordinate, symmetric in the variable xj, right? Symmetric. And furthermore, if the set A that you start with is already symmetric with respect to some other coordinate, then this doesn't change that, right? It's very easy to check that as well. So that means we can do the following. We can start with A, and then we can Steiner symmetrize it with respect to the first coordinate. Yes? Yeah, well, if A is not compact, that's okay. You can still, but you have to get in a bit of a mess. You've got to check that this is Lebesgue measurable, for example, and that's not true unless A itself is measurable. So it becomes a bit of a mess. It's better to work with compact. Yeah. Did you say convex?
No.
Compact? Convex. I'm sorry. Sorry, I misheard. So convex, what was your question then?
I was asking about the case that A is convex but not convex.
Yes. Well, okay, but here that's a case like this, right?
Because if the shape is not like one product.
Well, this could have holes in it, for example. Is that what you're worried about?
Yes.
Yeah, well, that's still fine. You still do the same thing. Same thing still works. You use the Lebesgue measure of this. This is no longer an interval, but it's a union of intervals, and exactly the same thing. So yeah, I'm not assuming anything about how nice the set A looks, right? Could be quite bad. But in any case, this set looks much nicer because it always has intervals in the xj direction. Yeah. Okay, and so we can do this. We can start with a set A, we can define S1 of A, and then we can do Steiner symmetrization of that with respect to 2, and we can keep doing that until we've used up all the variables. Now let's call that set A tilde. Well, it's still got the same Lebesgue measure. Oh, and the other thing is, this is part of this week's assignment, prove that the diameter, so it doesn't change the Lebesgue measure, but prove that the diameter of SJA is less than or equal to the diameter of A. That's another fact. That's not quite obvious, but it's true nevertheless. And I'm asking you to check that in this week's assignment. So we get a set A tilde this way. Then so that means that A tilde will be symmetric with respect to all the variables, right? So that means that x in A tilde actually implies that minus x is also in A tilde, because it's symmetric with respect to all the coordinates there. So that's good. What else? Well, we know that the Lebesgue measure is the same. We haven't changed that. And the diameter of A tilde is less than or equal to the diameter of A. Well, that's great, because now our false proof works. Because if x is in A tilde, then then the length of x is a half of the length of x minus x. But that's less than or equal to the diameter, because both these points are in the set. So this is less than or equal to a half the diameter of the set A tilde. But in turn, that's less than or equal to a half the diameter of A, because as I said, this process does not increase the diameter of the set. So we get that. So that proves, now our false proof works. It says that it says that A tilde is contained in a ball of radius diameter, half diameter of A. So ln A tilde is less than or equal to omega n times diameter of A over 2 to the nth power. And this is equal, remember, this process doesn't change the Lebesgue measure, so this is still ln over A. Yeah, so that's the isodiametric inequality. Very nice fact. So we have this. So now let's complete the proof now of the fact. So let's see, what did we prove so far? We proved that we proved so far this inequality. Now let's try proving the reverse inequality. Once we've got the isodiametric inequality, the reverse inequality is rather easy. So proof that the reverse inequality holds. That is that ln A is less than or equal to hn delta of A. And let's do that. Well, take any sets C1, C2, etc., with A contained in a union, Cj, take 1 to infinity, and diameter Cj less than delta, then Ln of the union of the Cj's by subadditivity is less than or equal to the sum and now we can use the isotometric inequality. It's less than or equal to the sum, less than or equal to the sum omega n times the sum j equals 1 to infinity diameter Cj over 2 to the nth power. And of course this is bigger than or equal to Ln of A because A is contained in the union. And now just take the inf over all such collections, right? So take inf. And that immediately gives that, if you take the inf, you get that Ln A is less than or equal to Hn delta of A. So that's it. So you get equality. So that's very nice. So there's no difference between Lebesgue measure and n-dimensional Hausdorff measure in Rn. But of course, so you can sort of think then that, in fact, the way to think of Hausdorff measure generally is to think of it as the natural generalization of Hausdorff measure. In fact, for example, we'll show when we start talking about submanifolds of Rn, we'll show that indeed n-dimensional Hausdorff measure on an n-dimensional submanifold of Rk, so we take an n-dimensional submanifold in some Euclidean space, take the Hausdorff measure, n-dimensional measure, that turns out to be exactly the same as the ordinary volume of that submanifold in the sense of Riemannian geometry. So Hausdorff measure really does give you the natural analog of Lebesgue measure in a wide variety of spaces. That's the way to think of it. Okay, so let's see. That's the story about the definition of Hausdorff measure and the fact that it does indeed generalize Lebesgue measure. Now let's talk about densities. All right, so densities. So define the upper and lower densities. So here X is a metric space. And mu is any outer measure on X. And then define the upper and lower densities as follows. N-dimensional densities. You define, if for any set A contained in X, you define theta n mu AX to be the lim sup as rho goes down to 0 of the measure of A intersects the ball of radius rho divided by the Lebesgue measure of the ball of the same radius, omega n rho to the n. So this is sort of somehow comparing the mu measure of A intersect with the ball of radius rho with the Lebesgue measure of a ball of radius rho in Rn. Sort of a comparison. And you take the limb sup of that. And likewise, the lower density. Oh, by the way, limb sup, remember, means that you first of all take sup over a small interval rho less than delta. So you take sup over rho less than delta of mu A intersect B rho x over omega n rho to the n. And then you take the limit of that as delta tends to 0. Now notice that limit does exist because the sup is a decreasing. It's an increasing function of delta. So in other words, it decreases as delta gets smaller. So this. Oh no, this. Well, this doesn't. This can be doing anything, but. Yeah, no, that's right. The sup of this quantity over all possible rows in the interval 0 delta increases as delta increases, obviously, and therefore it decreases as delta decreases, and it has a limit. Of course, it may be plus infinity, but that's, again, fine, as usual. So that's the upper density, and the lower density is similar. And inf, as rho goes down to 0 of mu A intersect B rho x over omega n rho to the n. That is equal to the limit as delta goes down to 0. This time it's the inf. N0 delta of mu A intersect B rho x over the same quantity, omega n rho to the n. So again, this one is, as delta increases, this one decreases. In other words, as delta decreases, this increases, but the limit, of course, exists, therefore it's monotone. So these make sense, and they're called the upper and lower densities. If they're equal, you simply drop the star. If theta n star equals theta n star, then we write just theta n, mu ax. Okay, so there are some things about this upper and lower density function. One important fact about it is that claim if all Borel sets are mu measurable, then these functions, notice this can be viewed as a function of x. If we fix mu and a, it can be viewed as a function of x. Then theta star n mu ax, and also the lower density function star n mu ax are Borel measurable functions. I don't think we'll need that anytime soon, but it's an important fact, and if, you should take a look at the argument. The argument's fairly easy to check that, surprisingly, because it just uses the fact that this top line here is actually an upper semi-continuous function of x. If you fix rho and just vary x, it's an upper semi-continuous function of x. That doesn't require any facts about mu, except that the balls are measurable, and so that's why you would have to assume that all the Borel sets are measurable to check that fact. So it's a fairly elementary argument, but I don't have time to give that here. So keep that in mind, but I don't think we're going to need that, at least not soon anyway. So on the other hand, what we will need on many occasions is the key theorem about this upper density function. It's called the upper density theorem, very important theorem. So let me state that theorem. The upper density theorem. And it says the following: if mu is if all x is any metric space, and mu outer measure on x, any outer measure on x, such that all Borel sets are measurable, then the upper density of mu a x, one more hypothesis, and a is mu measurable and of finite measure. Anyway, finite, then the upper density, upper n-dimensional density with respect to mu a and x is actually equal to 0 for hn almost every x in the complement of a. You've got to stare at that for a while to see the logic of it. You've got to keep in mind what the definition of this thing is. It's the lim sup of a ratio mu p rho x intersect a over omega n rho to the n. So you could sort of convince yourself that this somehow looks like one of the terms in the n-dimensional, in the definition of n-dimensional Hausdorff measure. So if this is bigger than or equal to t for some t, and that means for small enough rho, this top line is almost up to a small error is bigger than t times omega n rho to the n. And if you sort of think about taking lots of balls like that and adding them up, you sort of get the measure of A by taking suitable balls on the right side, and you get T times the Lebesgue measure on the left side, and somehow there should be, so that sort of fuzzy reasoning maybe convinces you that there maybe should be a connection between Hausdorff measure and the upper density of this abstract measure mu, but it's not clear at all. It's not until you see the proof. This is not at all obvious. It's once you see the proof, you get the idea that it's maybe not so surprising. Okay, so I'm going to give the proof of this later. We need a couple of tools first, 2 lemmas in fact. So proof later. This is certainly one of the key technical tools that we'll need. We use this in several different results that are to come later. So this is an important lemma. It's the main lemma about densities. By the way, notice that in the special case of Lebesgue measure, it says that the upper Lebesgue density if you take Lebesgue measure here in Rn, so you take the metric spaces Rn and X, then this is obvious because in that case this is just the n-dimensional density of the set A, which we know is 0 for almost every X in the complement. So that's sort of a known result. We'll reprove it as a special consequence of this actually, but nevertheless, at least this does agree with what we know already about Lebesgue measure. So that's one point to keep in mind. So let me describe the tools that we'll need to prove this. The first one is the so-called 5 times covering lemma. Five times covering lemma. And that says the following. Suppose let script B be any collection of closed balls. In the metric space X, and one condition, and suppose that the sup of the set of diameters of these balls, when you consider all possible balls, the sup of the diameters of those is finite. So you must have a fixed bound on the balls. Otherwise, there's obvious counterexamples to what I'm about to say. So you assume that. Then there exists a pairwise disjoint subcollection. Remember, PWD is an abbreviation for pairwise disjoint. Subcollection B prime contained in B, such that the union over all the balls in B is contained in the union. Now we'd like to say it's contained in the union over all the balls in the pairwise disjoint collection of B. Well, obviously that's ridiculous, right? If you have a collection of balls overlapping like this, you can't take a pairwise disjoint collection which contains the original collection, obviously, in general, unless they happen to already be pairwise disjoint. But the next best thing is true. Namely, you just have to enlarge each of these balls by a factor of 5. So here the notation. If B is a ball of radius rho and center at x, then B hat means the 5 times enlargement. That's the ball of radius 5 rho with same center as the original ball. So as long as you're willing to enlarge the balls in that way, you can get a pairwise disjoint collection. So somehow that union, you can pick out a few of these balls. Well, this picture's pretty easy. I can just take that one ball there. It's not hard, but you can do lots of complicated pictures. And a common question people ask is, well, is there any particular significance to this number 5? Well, that's just really a convenience. If you work a little harder, you can prove that you can put 3 plus epsilon there. But what would be the point, right? It just complicates the proof. By the way, it's false with 3. There is no 3 times covering lemma. There's an easy counterexample. You can see it in the text, actually. There's no 3 times covering lemma. It's false. So this is the 5 times covering lemma. And I can at least start the proof. Maybe I can tell you roughly how the proof goes. We don't have time to do the details, but it's pretty straightforward. You simply call this thing R, this supremum here, let's call it R, capital R. Call that supremum R, and then you subdivide B into sets where the diameter is between R over 2 to the j minus 1 and R over 2 to the j. So this is the set of B and B such that the diameter of B is less than or equal to r over 2 to the j minus 1 and bigger than r over 2 to the j. So you see that divides the whole thing up. That means that B is indeed equal to the disjoint union of Bj. So that's just one way of dividing the whole collection up. And then you simply use Zorn's lemma to take a maximal pairwise disjoint subcollection of B1. So Zorn's lemma implies there exists a maximal, I'll explain precisely what I mean by that in just a second, maximal pairwise disjoint subcollection of B1. Now notice B1 is diameter B less than or equal to R bigger than R over 2. And maximal means, let's call this subcollection B1 prime. Contained in B1. Let's call it B1 prime. Maximal means that if you add one more ball, it breaks the bank. That can no longer be pairwise disjoint. So this is not pairwise disjoint for every B in B1 minus B1 prime. For every B in B, minus B1 prime. So you can't add one more ball that you haven't already got. It will cause you to get them. Notice not pairwise disjoint means that B intersects B prime is non-empty for some B prime in this collection. So that's the first step of the proof. I think you're familiar enough with the use of Zorn's lemma to justify that. You just use the fact that you look at all pairwise disjoint collections of balls in B1. That's a collection, that's a set. And that's a partially ordered set by inclusion, partially ordered by inclusion. And if you take a totally ordered subcollection of pairwise disjoint balls, notice you can take the union of those balls. If they're totally ordered, you can take the union of all of those, and it's still pairwise disjoint. That's only true if it's totally ordered, though, so that every one of the collections is contained or contains the other. So that's exactly the conditions under which you can apply Zorn's lemma to give a maximal element. So there's nothing much involved in that. And that's the first step of the proof. We'll continue it next time, I guess, but the next steps also involve using maximal subcollections, but using these sets Bj now. But you've got to be a little bit careful. It's an inductive procedure. It's only a few lines, the proof, but we do have to be careful to do it correctly. So I guess we'll continue there next time.